Okay, so hello everyone. So most of you will meet again in the classroom. Okay, so I think you're from the material science, right? Okay. Okay, so all right. So for today's class, I would like to share with you my plan, okay, my syllabus, and also what we are going to cover, and a little bit introduction to the course itself. Okay. Let me start. Yeah. First of all, if you have the time, you can scan the QR code, because I think in the middle of the presentation, as usual, you might see that I would like to asking some feedbacks or comments in the middle part. Okay. Yeah, I think we can start. Okay, we'll be waiting for a few minutes. By the way, this course is supposed to be the continuation from statics. So, have you taken statics? Statics? Yes, right. Okay, let me continue here. Okay, mechanics of materials. So, the course itself, the name, mechanics. So, of course, we are going to see some property that is mechanical property related to some classical physics. So mostly, if you remember some statics courses content, that mostly you need to draw like a diagram, right? The stress distribution and so on and so forth. We are going to do that again in this course. Okay? So I hope you still remember some parts of it. I will review for some parts. Hopefully we have time. And the second part of the name of the course is the materials. So we are focused on how the materials behave mechanically. For example, some foam is just a regular foam. If I stretch this, okay, it is like small amount of displacement. Okay, so let's say it's like the shape is like the normal shape is like this. Okay? If I take this and I release, it goes back. Okay, it goes back. Although it's not really straight. Okay, and then if I twist, I should give some line here, so you can see some slight twisted here. There's some examples that probably how we are going to see how the materials will behave. Okay, and every materials they have different property, right? And that will be also in our courses as well. Okay? Although it's not really that super extensive. For example, we are going to see some simplified assumptions, okay, for some methods. Okay, just to know, okay, most of you already know me, so yeah, my name is Emmanuel Purama, and yeah, I'll be your instructor for this course. So I studied material science before, so all the courses that I will teach that related to material science, I will put effort to give emphasis on material science perspectives. Okay, just I would like to know. Okay, so I would like to know. Okay. You could choose which one you pass And if you haven't, it's okay. Just tell me so I know your background. I just want to know the number, how many pass, or maybe it's a good job, probably. Okay, barely pass. Why? Whoever. Anyone did a good job? No? I think great job. If you get B or B plus, I think it's already good job. Not to be like you need to be perfect like A to be a great job. I think B or B plus is already good. Okay. Anyone fail? Still maybe not get retained. Oh. You need to take again.
Yeah.
Next semester or
next
semester. Okay. Okay. Okay, what do you remember about statics? What do you remember? I believe you remember mostly the teacher or the professor will draw, right? Will draw like a beam like that, right? You give some here, right? Or do you remember if I slice this, what will happen in the internal force inside, the resultant? You see this, and this, right? You still remember that? Okay, I think we need to review a little bit, okay? we need to review a little bit, okay? But don't worry, okay? Don't worry. This course is, the content, the principle is not that much. The content is mostly, they will have more like examples because every connections with beam, like with the, if you see a bridge or buildings, every quarter of them, they will have some mechanical included, right? That we need to know how much force we need to take, or how does this building retain its shape, okay? If it's maybe earthquake, or maybe if there's any typhoon, right? So we need to also imagine that happen. And of course, as simple as if I put my hand in this board, I put some pressure, and if you imagine becoming the board, you'll feel the pressure. But if you want to stay here, if you want to stay in the shape, you need to give back the pressure, right? So we say that this is a reaction force, right? Like when you, maybe if you push your friends push back, right? Okay? So something like that. So it's mostly that is from statics. But we are going to use that again in mechanics of materials and combine them with the mechanical properties and all the, so it's more advanced than statics, okay? It's more advanced than statics. This course, mechanics of materials, if you maybe have, looking back, some textbook, maybe old textbook, or maybe different maybe in different university, sometimes they name the course solid of mechanics. I think statics 2 is also similar to mechanics of materials, or strength of materials is also the same course as this course. Okay, so if you want to look somewhere, that's the same course. Okay, I think I will skip that for a while. So what you need. And what you need to know is about classical physics. I advise, my suggestion, prepare a ruler, especially for exam. Okay? It's really helping. It's really helping. Just for drawing we call the free body diagram, if you remember, in statics. Of course, statics. some statics content. Calculator, I think for this course is a must. Okay. And practice. Okay, we will have more practice in this course. Okay. I think if you use the digital device for drawing or for writing, I think you already have like automatic ruler. But I think ruler is for at least for your exam. Just my suggestions. Okay, my system for our course is 20 for quiz, okay. Midterm 30, final 30, activity attendance 20. We will see how we will have our activity in class, or maybe after class, like maybe homework, or probably homework. Okay. Homework is just to make sure that you're working on something. I don't mind if you work together, as long as you learning, okay, if you study, okay? Because I believe one student usually asking the students who he knows smarter than him, or maybe need more experience than him, and asking something. But I hope you can teach each other, okay? I think that's one way to learn. Quiz, midterm, final, activity attendance. For quiz, depends on how many chapter we have. Usually, if we take every chapter, maybe too much. Maybe every 2 chapter or every 3 chapter. Okay. We will see. Okay, for the quiz. So mostly this is what we are going to cover. So introductions, and then until the torsion chapter, and then midterm. So in between this chapter, maybe 1 quiz, okay, and maybe 1 quiz here. So maybe 2 quiz. Okay. But if we need more quiz, maybe we can have. If we want to have maybe the early quiz or midterm, maybe not really good score, maybe you need to have more quizzes here. We can adjust that. And then final exam. So midterm exam is the first half, okay? And final is the other one. Okay? But this other one is automatically included, because some definitions may be included here. And do not worry about the name, okay? The terminology, the name, the terms. Okay? What I want you to have in this course is the first thing is good visualizations, good logical thinking. I believe that is 2 basic components to understand this course. Okay. So today is this, right? Introduction, syllabus, and then the next Friday, right? Friday morning. So your class, evening, and then morning, evening, and morning. Okay, that's good. Okay. Principle, we will see some principle. Actually, some principle I will try my best today, okay, just to have some review. And then March, still principle, but I think this week we can finish, so we can have a stress strain here, and we can move on. I think we can move on faster, because at the early part, it's not really much that we can talk to, not much discussion also. More discussion is in this stress strain and the axial deformation. That is mostly we are going to have some problem solving cases. This stress strain for this part is actually the last chapter in the textbook. I haven't mentioned the textbook. Have I mentioned? I think I haven't. I have the textbook. Let me just show you. This textbook is this. Mechanics of Materials, the 4th edition, by Roy Craig Jr. and Eric Tellef. This is the SI version, the unit, all the standard unit. If you look on, I think there are some, I'm not sure if you see some older version, the content is the same, but maybe different question and different units. But all the things inside are the same. Okay, and then quiz 1 here, or maybe earlier, it depends on how fast we are going through. And then move on to the torsion. And still torsion and then midterm. Okay. So the midterm exam, after we learn torsion, and we can have a midterm. Okay. So if we finish the early part faster, it means that we can have more problem solving in classes. So we can have more practice. And then after that, the transformation of stress strain and then equilibrium of beam. So we are going to observe some phenomenon on beams. And then stresses in beams, deflection, combined loading. There's some method to this, but I think if we need more time, I think this need to be two class. Okay. But then it's quiz, another quiz, and then continue, and then this is, I think, the last part, the energy methods. The energy methods. It means that we are going to observe the mechanical behavior through energy approach. Okay? Through energy approach. That means if you learn material science before, or at least in the introduction of material science, you learn about the behavior of the stress and strain, right? You remember. And if you remember correctly also, if you look at the area below the curve, it's actually, if you, with respect to the volume, it is actually an energy. Okay? Energy, you can say that's energy. So we can also use that in our course here. And we're going to talk also that stress strain in materials science, okay, if you still remember that. And then last part here is final exam, okay. And this week here, I still not, no plan in this week, but if we need, we can have special class in this Friday just for exercise, okay? For preparing the final exam, for 1 hour class here. But if not, then we can skip, because I know some of you having other final exam as well, right? Probably between this 2 weeks is final exam, right? So we can skip this and focus on the final exam on the Tuesday. Okay, so this is 3 fundamental in solid mechanics or in mechanics of materials. So first is equilibrium. Equilibrium means any formulation related to the mechanical phenomenon in one material, we need to first write it down. Okay. Of course, in statics, because we assume all is rigid, all is statics, so it's just it's by itself. So we just say that, okay, the sigma f for x-axis is 0 and sigma f y is 0, and then it's the moment at some point, depends on what we observe, it's 0, right? And for the first half in our course, we are going to use the same thing as in the statics. We are going to use the same thing. And then material behavior. Okay. Material behavior. Is the material flexible? Is the material rigid? Okay. That is going to determine how the the solution will be if we are given some conditions. And then geometry of deformations. How would it deform? Is it deformed like elongated and maybe deflected? How much deflect? So it's also affected the solution that we can apply. And lastly, okay, these three fundamental why we need to take this course is because in material science we need to understand the behavior of the materials, and the basic parts to understand how materials behave is the mechanical properties, because it's easily to observe, and in mechanical property or in sense of mechanical, the science is well established. They already have like a solid foundations for us, for you, for students to understand what really happened. Okay? Compare with, if you compare fundamental concept in material science, usually materials defined by metals, right? Ceramics, polymer, composite. Right? The most well-established science is metals, because it's already established long time ago. Ceramics maybe after that, and the younger one is the polymer, right? I think if you've taken the polymer class yesterday, I would talk to you that if you live in 1910 or 1920, people doesn't really know what polymer means. If we speak, do you know polymer? They will, what is that? But they know plastics. They know some rubber, but they don't know the word polymer yet. Okay, so it's the youngest one. And in metals, the way we understand the mechanical property is the same thing as we will learn in our class today. So the stress strain curve, the tensile strength, all of that is already established. People already invented, found like long time ago. So for us today, it's actually easier to follow. Okay? And again, as I mentioned in the early class, that in this course you need to have good visualization and good logical thinking. Visualization means you can transform the questions into the drawing, the schematic drawing. Okay. So three fundamental solid mechanics. So mechanics is a physical science that deals with condition of rest or motion. Okay. So that's mechanics. But for most of the parts, in our case, in the first half, we are going to observe statics. That's why you take the statics course, right? You take the static course. And it feels weird when I'm using this. So for statics and dynamics, acted by force or thermal, but mostly by force. If you look on the course, okay. So as I mentioned, so mechanics materials known also as the strength of materials, mechanics of solids, mechanics of deformable bodies. They are the same lecture. Okay? They are the same lecture. So if you find in the textbook that this is the title, that's the same thing. They're the same thing. Okay. Okay. Maybe you can write some comments, suggestions, expectations. Okay. If you already taken this course before, maybe you can have more or something to say. Okay, yeah. Yeah, feel free to write anything, okay? Okay. Okay, more time to the notes, okay. Okay, I think enough. Do we have more here? Okay, I will switch to my my notes here. Okay. So this is the first lecture. Okay. So what I want to show you first is what we call the finite element analysis. I think this is usually on mechanical engineering, but this is just to show you, okay, how the mechanical or the mechanics of materials will help you to overview. Okay. So in the finite element, so the method is actually, so if we have, okay, this is the material. Okay. So imagine that this material is composed of a small parts that we call nodes. Okay. So it's small parts. So we can connect the nodes, okay, and then with some computational, using some software, we can design how the stress is distributed. And of course, from this picture here, I think you can assume or you can predict which one has the higher stress, the green one or the red one? Green or red? Red, right? Okay. Intuitively, you can say red, right? That's the powerful of colors. So this method really useful for studying the how the stress can affect your design, and you can test the design whether the design is allowable or not, okay, depending on how the force will be. And this software, usually the Nastran, ANSYS, etc. We're not going to talk about that, but this is just to show you some information. Okay, this is also another the stress concentration. Okay, how this red one here. This is the mechanical latch for a space shuttle. So it's for opening, okay, the latch. So if you see, this is the sides. If you see that this part here has the most stress. Now, of course, because that's how he can hold some forces, right? And if you see the other picture here, so this is analysis on this stress concentration due to a hole here. And you see that here there are already high concentration of stress. It's logic, right? It's logic. If you have a hole, like what kind of material? Maybe if you had something, maybe in your phone, okay, in your phone, if you have a crack, already like a small. Of course, the crack will propagate it, right? If you give stress, more stress, lately it will break, right? It's the same thing. If you have a hole here, it means that if you give stress more and more, this hole will have some concentrations, right, for the stress. Stress is going to increase, and eventually it will have a crack here. Okay. So you can also see this analysis. It can predict how the stress will affect your design, how and where the crack will be. Okay. So if we know some things, like from some design, like, oh, the force is from here, so what will happen to our design, how we can prevent it, that's how this can help. Okay? The design can help. Okay? And also the color will give you analysis. Okay. Okay, just a brief information why this is important. Okay. Okay, now look at here. Okay, there's a gentleman in a diving board. Say it's diving board. He wants to do jumping, and then although there's no water, let's assume that he will jump to water. Right? Okay. Okay. So first we define what is this. Okay? This is a board, and then there's something like a circle. So perhaps you can assume maybe there will be. We can imagine that there is reactions, right? And then there's something here. We have it has zoom in here. Okay, it has some screw here, and maybe this is a fixed design. Okay, so it's a fixed design. And then we have some distance here, and then there's this is a delta. We use this for displacement. Okay? We use this for displacement. And some thickness h. Okay? Of course, the man has a weight that needs to be reacted for both sides. Okay. Okay. So, given this picture, okay, if I ask, okay, what weight would cause the diving board to broken, okay, and where would the so if this is the diving board, okay, and if the man, for obvious reasons, if this weight is too high, that makes the diving board broken, can you think the place where it would take a place? Where? Do you think where? Can it be broken here? I think no, right? If you see the way it's deflected, probably here. Okay? Logically? Okay? So something like that will be in the future, like given some part of problems, some conditions, some weight, some force, weight, or any forces, and then you need to assume how the other environment will have a reactions to that external forces. Okay? And then of course we need to also see is there any relationship between this, the displacement, the weight? Is there any relations? Okay. And we are going to cover that as well. Okay. And then maybe we can also think what kind of materials we need to have here. Okay. 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 So again, let me just confirm three concepts. Okay. So equilibrium, geometry, deformation, and material behavior. Okay, for the equilibrium, let me make this click here. Usually we are going to see that the sum of the force, the resultant, the sigma, is going to be 0, and the moment at some point, let's say the point at 0 point, is also 0. So this means the body is in equilibrium. Okay? And we can also think in the Cartesians. Okay? For example, we can say in the x-axis and the y-axis, okay, it's also 0. Or if you want some three dimensions, we can also say in z. Okay? But for the early part, we can just have 2 dimensions. Okay, aside from the equilibrium here, because it's related to force, we also need to see that there are some external loads. Okay, I forgot to put some picture here, but let me just draw for you. Let's say this is our deformable body. Deformable body. And let's say this is, we call this concentrated force. And let's say you can imagine this like a cylinder, and we can imagine that there is concentrated couple. Moment, concentrated couple. And then we have, let's say here is, we call this a line load. And let's say if we have let's imagine this is taking some surface here, and from the surface it also gives some forces here. My arrow is really bad. Sorry. Okay, so we call this the surface load. So the load goes pushed through the surface. Okay. Okay. This is just an brief intro. We are going to elaborate more later. Okay. If you want to take notes, I think you can, but if you want to skip this one, it's okay. This is just a brief intro. Concentrated force, concentrated couple, line load, surface load. And sometimes if you see the diagram, let me give some analogy. If you see that if usually in physics, or maybe in statics, usually say here, right? Maybe F like that. This is what we call the resultant force, right? Resultant force. So if we give some force, of course there will be some distributed force here, okay, along the area. And I think you also learned this in the statics, right? Sometimes you see the distributions like this, right? Or maybe this is wrong. It's supposed to be force here, it's supposed to be here, right? It's distributed like that, like a triangle. And then the way we understand this part is through the area of the triangle, right? If you remember. Okay, later we can have discussions. So today is for the introduction. I just want to share some terms, definitions. Okay, not really going into the principal chapter in the in our course, but this is just like basic information. Okay, and then another important thing. Okay, well, wait if you want to take notes here. Okay, let me continue a little bit, just to show you some of the support reactions, okay, or member connections, okay, because we are going to see this a lot. Okay, we are going to see the roller support, like usually a circle or a triangle with a circle below, which means the force will be having a reaction force like this. The required force for couples, if this couples. And then if we have a cable or a rod or wire, then usually we have an angle and we can have this like a tension, like a tension, like if we pull the this rope or this rod. Okay. And if this is a pin support, we are going to observe that there will be a two reaction here, and there will be some resultant, okay, from these two. So there will be resultant here. This is also going to here, right? And if this is a cantilever support, which means it has a fixed end. Okay. This pin support we can move. Okay, so that's why it has this reactions. Okay. But here, there's no movement. So like this, you put maybe the metals, maybe put in the wall, okay, and maybe use cement or maybe just put and then leave, okay. It means because there's nothing to, because here we can move freely, rotate, right? And because there is no rotation here, if we like have to imagine that, okay. Okay, imagine if this is going to put here fixed end. If I want to rotate, how would like this to be react? The other way around, right? Okay. That's why we have the moment. Okay, I hope you get it. So every time the problem says any cantilever support or the picture is not having anything and just put there, it means it's fixed end. So you need to imagine that there will be some moment reactions. Okay. Okay. The two dimensions is very basic, and you need to be familiar with the concept. Okay? And I think in statics, I think it's simplified, right? Not really that much we talk in statics on the support sections. But here, there's a lot of considerations. And if we look at the 3D reactions, we have ball joint and cantilever support. The same. Okay, ball joint. It's like if you have like a figure or maybe a Gundam. Usually they have something like this to put in their shoulder here, and they can move like this, right? So there's no moment. So the difference between these 3 dimensions and 2 dimensions is that in 3 dimensions, of course, we need to have another axis. But I think in our course we have a lot in the 2 dimensions, because that's more basic and easy to assume. 3 dimensions sometimes is very hard to imagine. We will have, but I think not really as much as the 2 dimensions. And for the fixed end, it's a similar way with the 2 dimensions. The difference is, of course, we're going to see in the 3 different sections. Because if we move this around, it's already fixed over there, then we cannot do anything. In the ball joint, we can freely moving the object, right? Freely rotate, right? So there is no moment. Okay, this too is the reactions end, okay, at the end of the beam usually. For the next one is the connections. Okay. And the same, there's only two connections here: the pin connections and the rigid connection. Pin means that you can freely move, okay, rotate. I mean, through this pin. Okay, imagine you have like if you put some nails and then you can rotate. Okay, if you can imagine that. And the rigid connections means that it's like a fixed end. Okay? It means you have the moment. So you have the moment. How the moment behave and how we can figure it out, how to solve the problem. That will be the next step. Okay. And if you see, the other important thing is we can imagine this connection here from the perspective of one beam here. That is the axial beam. Okay. How it would like to have the reactions here or here, right? And then the reactions on this other beam. Okay. That the connected one here. And of course it has this reactions because of the we need to have the resultant 0. Right? And also here, you can also see or observe this one here, the axial one. And the reaction is through here, because the shear goes here, we have the force here, and then the moment. Oh, we say this one is the shear one. We are talk about that later. And we can also see the other part here is the opposite of this part, because we want to have the resultant 0. Okay. Okay. I think in statics you're already familiar with the free body diagram. Free body diagram, I think. Yeah, should be in statics. Is that free body diagram? Yeah, free body diagram is a way to simplify our forces, okay, into only, like for example, if we have this system, we can simplify this area. So this one. So this will be our free body diagram. But I think I will just explain on the next slides, more complete. Okay. Or anyone, do you have any textbook already? Maybe from your senior? Okay. I think if you look on the internet, you can find some, but I'm not sure whether it's legal or not, so I'm not suggesting to do that. But if you want to look and just to observe, you can do that. Or you can ask your senior or maybe your other friends maybe that have learned this before. Okay. Okay. Now if you look here, okay. For the first part here, doesn't matter if you not really writing all the notes is okay. I think the important one I will give some emphasis. Which one I think you need to write this down. Okay, this one we call the two force member. Okay, because we have this point here, and then we have this is one beam, the other one here, and we can observe let's say from this x distance x here. Okay, let's slice this up, and what we have is this. Okay, so we can have this. I think this becomes a standard. I think in statics also you have called the force here, or the normal force, or the normal stress, if you will, and this is V. Do you know why use V? You know, the way to understand why it's V, I'm not sure whether it's official or not. It's kind of like a scissors. So it's like cutting something. Okay, so it's like because when you cut paper, you're shearing the paper, right? So it's like a shape of a scissor, V. Okay, and it's the F and then moment here. Okay, this is the first body. The other one we can also draw the opposite of the other side here. Now, of course, we have this P is coming from the B here. And why it goes here is because the resultant of this, because this P here we can make it through that, and maybe I will just use my iPad. So we can make this, and if we have that angle here, we can make this P cos theta, P sin theta, right? And of course, this will react to this B, and we say Bx, By, okay? And because there is no other conditions, then we can take the resultant, and the resultant should be equal with the P. Okay, so that's why it's P here. Okay. Okay, the other picture that I would like to share with you is this. So we have like a cylinder here, and we have an external loads here, and the resultants we will see from 3 different axes. So the y-axis, the x-axis, and the z here. Y, x, and z. Oh yeah, by the way, for this course, do you want to, like, I forgot to, like, before there was a break, right? You should, like, we have a break, but do you want to have, like, a break, like, in the future courses? Or no? Or having an early finish? Because I know that if this is done in the morning or in the afternoon, break is normal and I think it's really good, right? But it's evening class. Do you want, like, every time we have a break, do you want a break or we just keep going until we finish? Finish means that maybe we finish like 10 minutes early. Do you want that or early finish? Early finish, right? Because it's too a bit late course, right? Okay. Okay, another thing in this 3 dimensions, this T, we call this torque or the torsion. We have one chapter related to torque, I think later on. The My and Mz, this My and Mz, let me write here, My and Mz is or are they are called bending moment. Torque, we can also write torque as a twisting moment. Okay. And as usual, my lecture will be recorded, and now hopefully the audio is better than your polymer class. I forgot to adjust the microphone. Okay. Now the next thing after this one, the next slides is going to be how to use the statics. Okay, review your statics to solve some problems. Okay? Maybe 1 or 2, maybe 1 for today, and or maybe 2. Okay, now let's see this question here. Okay, this is, I think, still statics. A sign, it has weight 600 newtons. I think this sign's here, right? It hangs from a pin-jointed planar truss. Okay, this is planar truss. Okay. Use the method of joints to determine the internal axial forces F1 and F2 in members CDDE, which means F1, F2 is this, CD and DE. Okay. Neglect the weight of the truss member. So we assume all this is weightless, no weight. So we only concern the weight is on this side. Okay, and then the B question, use the method of sections to determine the axial force F5 in member FG. Okay. Now, method of joints, method of sections. I think if you're not familiar with the name or difficult to process, you can ignore them. And just focus on what the question is really asking. The question is asking CD and DE. Okay? If you remember statics, the first thing, if we want to solve this, is we need to isolate some members, right? Some members from all these picture, from all the picture here, we need to isolate the one that is significant, the one that is we want to know for the solutions. So let's isolate. Okay? So let's isolate the CD and DE. So we are going to isolate. Maybe let me write here for isolate. Let's say this is D. Okay. So actually method of joints is we are going to isolate the joints. Okay? So we are going to isolate this. Okay. So we are going to just draw this part. Okay. And then we can imagine that there will be some force here, which this is F1. And F2 here. So if we draw here, that we can see that this is what the questions want to answer, right? So F1 and F2. Okay. And then what's next? The given information, they give the length, right? They give length. And you can see all this on triangle. So maybe from the triangle, we can find something, right? So this is 1.2 and 0.1. Okay. Is that 3, 4, 5? I think 3, 4, 5, right? So 1.2. So we have, let me draw this triangle here. So this is 0.9 and 1.2. 3, 4, 5, right? So this will be 4, 3, 5, right? Right, 3, 4, 5. So why is it important? Because this is important to our force. Because we can have the angle right here. So we can imagine this multiplying with the component of the sine and cosine. Right? Okay, come back to this part here. So in D, if we look on the subject here, this is 600 Newton, right? This is 600 Newton. And how about this? How much this? If this is 600 and it goes by these two, let's say 2 wires here or 2 rods, how much the reaction force here? How much? Anyone? Get any guess? Just taking this Newton classics, sigma F equals 0, and let's isolate this. If this is 600, the total of course is to be another 600, right? So this is 300, okay? Agree? Okay, okay. Okay, don't be nervous, okay, don't be nervous. So this is 300 here. Okay. Okay, now from here, from this part, and let me just make this 4, 3, 5, right? And from our sigma F in x-axis equals 0, okay? Assume that the one that goes to the right is positive. Okay? Actually, the assumption is up to you. Actually, it's up to you as long as you understand. But my suggestion is you can go the right side positive, okay? Left side negative. Okay, easy to understand. Well, sometimes you can also switch up as long as you know the meaning and understand, the result should be the same. Okay? But let's just say, okay, the right arrow positive. Okay? So sigma F in the x-axis is equal to 0. So if we see from here, there is F2 and F1 is going to become 2, right? 2 component. So if this is theta, this is F1 sine theta, this is F1 cosine theta. So we are going just to x-axis. So only F2 and F1 cosine theta. Okay. So F2 is going to the right, going to the left, so it's negative. So negative F2. And then F1 cosine theta is also negative. F1 cosine theta is going to be, theta is here, right? So cosine is 4 over 5, right? 4 over 5. And it's equal 0, okay? And that's our first equations. The second equation is the y-axis. And for y-axis, we are going to assume that's going up is positive, right? So F1 sine theta, or sine theta here is 3 over 5, right? 3 over 5. It's positive. And then the other y is only 300, so minus 300, it goes down, so it's equal 0. So we can solve this, and we get, this is 300 multiplied with 5 over 3, so F1 should be 500 Newton. And from this 500, we could substitute to this F1 here. So minus F2 minus 400 is equal to 0. So F2 is negative 400 Newton. Or we could say, if you want to eliminate a positive negative, we could say F2 is 400 Newton, but it's compressive. Okay. And F1 is positive, right? So it's a tension. So T is for tension, or tensile. C is for compress. Okay. But if not, then maybe you can just write negative or underneath that. Okay, that's also okay. But if you want to maybe having more elaborations to C and T as well, fine. So F2 is actually compress, F1 is tension. And I think it's pretty logical if you see the picture. It slows down. And of course, the F1 is going to, so if you look here, the whole picture, this F1 will hold most of the part, right? Hold this weight. And this F2, well, from what we have there, it's negative. So it's going to compress this, going to go there, not pulling up, right? Okay. Okay, now what else? Oh, we have another questions. Use method of section to determine the axial force F5 in member FG. Okay, let me just wait for, if you want to write the whole thing here. F5 here, FG. Okay. Use the method of sections. So method of sections, basically, you are going to cut the sections. Okay. The first part, we cut only the joints, one joint here. This time, we are going to cut the sections. So how we are going to cut? So this is FG. So we cut here. Okay. So this will be we cut. Okay. And we are going to draw this part again as our free body diagram. Okay. So let me start with, there's C here, and then D over here, okay, and then E over here, and then it goes here. And then another F here, okay. Okay. And then, yeah, that's it. And then we have force here. Or let me just give some FG member here, and then the F is here. And let's say the F is going to be going to the left, F5. And then this F should be having a member here, but let me just cut that out and just write as a force, that is F4, sorry, F4. And then the other member is on here, let's see, and we can give them this F3. Okay, that's how you do the free body diagram. So the free body diagram, it depends on what we need to observe, what significant force that has in the picture, and because we want to know this Fg, okay, the force in here, and then if we just cut only the joint, we are not going to solve anything, right? Because we lack of information. We need more information from all the aspects, because we want to use at the later is the this length here for our couple moments. Okay. So let me just explain to you first, and then we can review. Okay, let's say this is B here, okay, up until B over there, and then imagine that you have this 0.9 length here and 0.9. Okay, so you have this is 0.9, and another part here is 0.9. And then on the bottom, we have here is the 1.2, and another part is 1.2. Okay, and again, this is 300 Newton. This is 300 Newton from 600 divided by 2. Okay, now we have three forces, and we don't know how much force for F5, F4, and F3. And if you remember, because we are given this length, why don't we use the moment? Okay. So we are going to take the moment. Okay, if you are given this, and you want to use the sigma moment, this is equal 0, how we should point our observation, which part that we are going to observe the moment. F, B, or B? I give 3 options. Who would think F? Okay, 1, 2. Who would think B? Okay, who would think D? Okay, remember, when we talk about the moment, when we want to make this come through, remember the moment is the force multiplied the length, right? Now look our force here. If we put our point in F, we are going to lose this F, right? If we put B, we are going to lose this. If we put B, we get everything. 1, 2, 3. At least we get, and we get to find the F, right? It's F5. Okay. Now, so from here, we are going to take this into point B, and for a moment, remember, assumptions is if we rotate clockwise, right? Clockwise, it's going to be positive. If we rotate counterclockwise or anti-clockwise, we are going to have a negative. Okay? Just assumptions. Okay? These assumptions will help you. Will help you a lot. So first is let's look on this point B. Okay, 300 goes here. Okay, this is B here, right? Okay. So 300 multiplied with 1.2. Okay. Oh, I should write the unit. Unit is important to be written, because sometimes there is some mistakes happen when you convert the units. And this is going to clockwise, right? 300, and then another 300 from D, 300 Newton, multiply with 1.2. 1.2 is 2.4 meter, and plus the F5. F5. Okay, and I think the question is just asking F5, right? Not asking F4 or F3. So I think we just finished and we can solve. And we got the F5. So if you calculate, F5 is negative 600 Newton. Or we can say the F5 is 600 but compressed. And then we can review our solutions. We see that F2 and F5 in compression, F1 is in tensions, and I believe that is appears to be, if you look on the picture, I think that is logically correct. If the question is asking another like F4 and F3, we can include another sigma Fx and sigma F1 equals 0, and then we can compute this. Okay. Because if we want to, if we want to calculate the F3 here, then the component will be having this two component depends on the angle, and then we can have this with the x-axis, right? And this F4 with the y-axis, and I think still have the same same conclusions at the end. If the question is asking F4 and F3. Okay, I would like to give you one more, but I think we will discuss further on the next Friday. Okay, any questions first? This is, I think, still statics. Still statics. Yeah, it's a review statics. So if you have learned before, I think maybe you will refresh some memory, maybe bad memory inside. Okay, let me give you one more, but this time let me write the question for you. Okay. I think we are not going to solve today, but let me just give you this this question first, and then let me try to draw. So this is pin connection there. Let's say this is A and this is B, this is C. It has a pin here. And then there's another pin, and supposed to be also attached to a wall. I don't know what kind of structure, but this is given like this picture. And this is D. Okay, the unit that I want to show here is not the SI, but it's more a British unit. This is going to be 5 inch. But on our exam, all will be SI, okay? This is just for practice, okay? And just to show you how we could work with this. And then what else? B, C, okay. So from A to B, is 6 inch. And then there will be some distributed force that goes by this triangle. Okay, we have a distributed force like this. And this is 1,000 pounds per feet. Okay. From B to some point here is 4 inch. Oh, I think the picture is going to have a different scale. So this is 2. So it's my drawing is not correct, but yeah, the number is 2. The 4 is shorter than 2. Okay, anyway, the question is objective. Find internal forces at point B. Okay, let me move a little bit down. Okay. Now what you need to do first? I think this distributed one first, right? Okay, first is we need to look for the concentration load. We know the distributed load is 1,000 pounds per feet for all this in the triangle shaped area, right? So we're going to use the triangle area. We are going to use triangle area. So area of triangle is half the base, right? Multiplied by the height, right? So we treat the 1,000 as height. So we are going to have the concentrated load as compared with the area of triangle is half 1,000 and multiply with 10, right? Then this will be 5,000 pounds concentrated load. So we can exchange this red line with just one single force here, 5,000. But the question is how to check the distance. I mean, where should I put this 5,000? Any idea? Yeah. 1/3 from the total here, right? So 10 divided by 3. So 10/3. Okay? You get it? So 10/3 maybe over here. So let me take this into 10/3. Okay? And if the distributed load is a rectangle, then it is just half. Okay? With a triangle, 1/3. Okay. Okay, and then this is two force member situations, right? So we can write our free body diagram. Okay? I think I will just end the lecture until the free body diagram, and then we can continue later. So let me just take one beam AC, okay, as our FBD, free body diagram. Let me write here. Okay, let's say this is A. We have, let's just say AX. Or maybe, let me just write first the loads. The loads is 5,000 here, 5,000 pounds, LBS. And then we have our beams DC. Okay, we can treat this DC as just an outside force in our FDD here. So this is AC. This is AC. Okay. And let me write with the maybe red color, or maybe just blue. So this is FDC. Maybe not really. Okay, FDC. And then we can write maybe A here. We can write the reactions for point A, so AX and AY, like that. Okay, and then because of this, you need to be aware whenever you see any diagonal force, it seems like a diagonal force, it means that you can extract this force into two components, right? It means you need to know the angle, right? Okay. And how to know the angle is because of this triangle, the big triangle, 5 and 10 plus 2, 12. So 12 and 5, this should be 13. So 13, 12, 5. Also a good triangle, right? If you remember trigonometry. So let me draw a triangle here. So there's an 5, 12, this would be 13, okay? And we have the angle is here, okay? So sine theta is 5 over 13, cosine theta is 12 over 13. Yeah, because the angle is over there, so I have to rotate my head. Okay, now we have all the components, so we can also draw here the angle here, and we can just say that this part here is FDC sine theta and FDC cosine theta. Okay, why I draw AY goes up and FDC goes up? Because from here, from the external force that we have in the questions, if we have like force goes down, your intuitions, or it should be reactions that follows, right? Reaction here, reaction there. Okay. Okay, and I think for AX and FDC, no problem at all. Okay, we can just draw at this. And then the next thing is the key for the statics. So we can write all down. And the sigma moment. We want to know the internal force at point B, which means that the point B is going to be around here, around this, right? So, which point you want to take the moment? I think either, if not A, then C. But if you take C, all these components will not be counted. Right? If we take this A as our observations for moment, we are going to get all the component here, right? For this part here, okay, and then we get the results. Okay. And then, so ideally, okay, every statics, if I'm not mistaken, and if you learned before, it will be easier if you calculate the moment first, and then calculate the F(x) and F(y). So calculate the moment, especially here, okay, for point A. And then calculate the sigma F. Okay. Okay, we'll continue this lesson next Friday. Okay. So, after here, think we can continue later on. So it's still half part. Okay, still half part. Okay. We still, because we find this, but the question is on the point B, right? We haven't yet reached B. We're still finding the F, this F first, FDC. And later we are going to look on B, the second part. So this is the first part. Okay, I will end this class and see you on Friday. And hopefully, in the future we can have more discussion. And if you feel a little bit confusing on the statics, and maybe some notes that maybe you forgot, we can have discussion. Okay, I will end the course and see you next Friday.